We move to the last speaker of this morning, Samir Mathur, who will talk about Fuzzballs, firewalls, and all that.
Thank you. And the remote. Control L for full screen, I said. Control L. You want to make full screen? And the remote, okay. You just move the keys. Okay. It hasn't come up there actually. Let's try the control again. I don't know. No. I think it's not picking the screen. Now it has come. Sorry. Okay, perfect. Okay, thank you very much for the invitation to speak at this wonderful conference. I'll be telling you about some work we have done over the past many years to understand the quantum physics of black holes. So as we have learned from Bekenstein and Hawking, the quantum physics of black holes is very puzzling. Do I get this to work? In particular, the formation and evaporation of black holes violates quantum mechanics. If we assume that semi-classical physics holds around the horizon of the black hole, and this is called the black hole information paradox. In string theory, however, there has emerged a picture called the Fuzzball paradigm, which seems to give a complete and consistent quantum picture for black holes, and my task today is to tell you what this paradigm is and how it comes about. In particular, it resolves the information paradox. To get a first pass at what the paradigm is, let us take a look at this cartoon of a black hole. Flat space far away, then you come here, you get some kind of a horizon, and inside the horizon is the interior of the horizon, and somewhere in there is the singularity. But when you look at string theory, you actually find that the black hole has a different construction. Far away, you still have flat space and then the curved space around the black hole as usual, but just before you get to the place where you expect the horizon to be, the space-time actually ends. And then the black hole has no interior and no singularity. So in particular, you get a manifest construction of degrees of freedom at the horizon, which is something that we would have liked to have all these years, because you think of the entropy of the black hole, you would like it to come from degrees of freedom at the horizon and so on. But here you actually get all that explicitly. So, and in fact, because there's the horizon interior, you also get rid of the singularity, which was always a problem. So the question is, how do you find this picture? And all you do is that you take string theory, you put together a lot of mass in one place, and you ask what kind of geometry it generates. And all the cases that we have tried, it never actually ends up making this structure. In every case, you get a structure like this. And then if you assume that this is what will happen for all the states in string theory, then we get a complete picture of the black hole, where we can now begin to understand all the things that we wanted to know about the black hole and all the various conjectures, like complementarity, because now you have an explicit construction of the degrees of freedom and the microstates which you wanted for the black hole. Of course, one question you can ask right away at this stage is, a black hole is a big object. A solar mass black hole is 3 kilometers in diameter. How did we have such a radical change of the structure of the black hole at the horizon of the hole? And it turns out there is an interesting answer that seems to emerge for that as well. The black hole actually has a very interesting property. It has a very large number of states given by the exponential of the Bekenstein entropy, which we know is a very large number. And it turns out the smallness of the transition amplitude from the black hole to any one of these states, we call these the Fuzzball states, that's a very small effect, and you might wonder why you would worry about quantum effect for something as big as a black hole. But the number of states to which you can transition, of course, is given by the number of Fuzzball states, which is the number of black hole states, and that is a very big number. And it turns out that this very large number of states gives a large measure factor in the path integral, which actually cancels the smallness of the transition amplitude. So in fact, the semi-classical approximation is broken at the horizon. Well, in top of that, you may still ask, do we have any way of recovering our classical intuition that if we go into a black hole to the horizon, we should keep going? And I will show you that indeed, you can get a small modification of the idea of complementarity that was proposed by 't Hooft and developed by Susskind. And then with this modified count of complementarity, you find that excitations of this Fuzzball surface can be mapped onto approximately the dynamics of infall into the hole, even though there is no actual place to fall into the hole. The last thing I would like to tell you, if I have time, is that recently the idea of firewalls has been much in the press and has also created a lot of confusion and puzzlement. Sometimes I've heard people mention the word firewall paradox, but there's no thing called the firewall paradox. The paradox part of it is just the same as Hawking's original information paradox. The paper by these authors, called AMPS for short, was titled Complementarity or Firewalls, and what it actually does is the following. You take Hawking's argument for the information paradox, you add one extra assumption, which I will tell you, and then what you get is that you rule out the idea of complementarity as proposed by Susskind. So if you did not believe in complementarity in the first place, then you are back to the information paradox. You don't learn anything new here. But in particular, Susskind was very particular about complementarity, and I also would like to believe that there is complementarity, and then one should worry about this argument. But as I will show you, the additional assumption that was used is actually questionable, and in particular, it does not rule out this modified kind of complementarity called Fuzzball complementarity that I had referred to. Okay, so with that introduction, let me start by describing the information paradox. So in quantum mechanics, the vacuum has fluctuations, so out of the vacuum, you can create an electron-positron pair, which then annihilates away, and the extra energy required to create the pair is allowed as long as the time for which it lasts is less than or equal to, this probability less than or equal to h bar. But if a fluctuation happens near the horizon of a black hole, the energy of the particle inside can be negative because the negative gravitational potential inside a black hole is so strong. And if this energy is negative and the energy of this particle is positive, then the total delta E can be 0, which means that the particle pair can last for infinite time. And in fact, these particles then automatically created. The vacuum around the black hole is unstable, and this is Hawking radiation, Hawking's discovery from 1974. So the black hole is slowly shrinking in size because the particle which went inside had negative energy, and the energy is collecting in these particles at infinity. The essential issue, though, is that the particle pairs produced by vacuum fluctuations are actually in a quantum entangled state. So the state of this pair is, if this was an electron, this would be a positron. If this was a positron, this would be an electron. So the state is like this. Using 0 for the positron, 1 for the electron, I can write it like this. So you can see the state of the particle outside is not defined by itself. This is a 1 if this is a 0, and this is a 0 if this is a 1. It's an entangled state. So the radiation doesn't have a state by itself. And then the problem comes Because the entanglement actually is very large. So if you produce n particles, then in fact there are 2 to the n ways in which the outside guys could be electrons or positrons, and on the inside it's entangled with what goes inside, these particles which fell in there, and they are in fact the mirror of what was sent outside. But now when the black hole reaches the end point of evaporation, you can see the puzzle. There are 2 possibilities. Possibility A is the black hole completely disappears and leaves you with the vacuum. At this point, there is no state which can be assigned to what is left outside, because these guys only had a conditional state. These would be all zeros if these guys were ones and so on, but there is nothing here at all. So what is left outside doesn't have any state for itself at all, and so we have violated quantum mechanics, and that was the claim of Hawking in 1975. Of course, nobody likes to violate quantum mechanics, so people started believing in possibility B, which is called remnants, that in fact the evaporation might stop when the black hole gets down to Planck size. But this also has problems of its own, because in a small region like Planck size and with a small energy budget like Planck mass, we have to hold an arbitrarily large number of internal states, and how can so many states fit in such a small region? One idea that has been proposed is there could be a baby universe hiding in here, but in string theory we don't have things like baby universes, and if we have only a Planck mass available, in fact there are very few states, so in fact remnants is not an answer. So then what is the solution? So you would think the string theorists would have had to worry about this long before, because string theory is a unitary theory of gravity, and as I said, you can't have information loss, and you don't get remnants. But it turned out that string theorists were sort of misled for a little while by a belief that the problem was not all that serious, and that belief came around in the following way. So in string theory, of course, you have black holes, and so why shouldn't you worry about the information paradox? But the belief which came up was sort of like this. Suppose you go back to this picture where you create the electron-positron pair in an entangled state. There can always be some small corrections to the entangled pair, because some quantum gravity effects may be due to some gravitational instanton effects, which could be really very, very small, but in fact you could make a small correction to the state of each pair. Now why should that matter? Well, the number of pairs you're going to create is of course very, very large. So in fact you might wonder, the leading order particle was connected by entanglement to was entangled with its partner, but if there are a lot of small extra entanglements that we missed at the leading order in the calculation, if somebody were to put those guys back, because so many particles are produced in the evaporation process, and then you compute the entanglement of the outside with the inside, maybe by the time the black hole evaporates, there isn't any entanglement left at all. So this suggestion was made by Mathur in 2001, but it was really picked up by Hawking, where he sort of developed this to the idea of using the Euclidean theory and putting in small exponential corrections to instanton tunneling. And he suggested that maybe there wasn't any paradox at all, because leading order answer gave the paradox, but subleading effects might actually cancel it. If that were true, then there was nothing to worry about all these years. But in fact, in 2009, I derived an inequality which showed that whatever you do with these small corrections, in fact, it cannot reduce the entanglement. In fact, if the corrections are of order epsilon, then the fractional reduction in the entanglement entropy of the outside with the inside is always bounded by 2 epsilon. This may look like a strange theorem, because we haven't even said what the small corrections look like or where they come from. That's why it was so hard to rule out this kind of an idea prima facie. But in fact, there's a lot of power in a theorem in quantum information theory called the strong subadditivity of quantum entanglement entropy. And in fact, using that, one can actually prove that if you make small corrections to the evolution of each pair, you cannot actually solve the problem. So all we have seen so far, the partial summary of what I have told you so far, is that Hawking's argument of 75 can actually be made into a rigorous theorem. Let me just state in a slightly condensed form here, and then you can look at the actual paper for full details. If the evolution of low energy modes for a solar mass, let's say the evolution from 1 meter to 10 kilometers, is normal at the horizon up to small corrections, then you must have either information loss or remnants. And which means that if you take something like usual gravity, where black holes have no hair, and this region around the horizon is supposed to be like this room, then in fact, you will have either information loss or remnants. You can actually make Hawking's argument a rigorous theorem, and all the ifs and buts are taken into account, and now you really have an issue. You either have to find hair and destroy the horizon, or you have some problem which string theory cannot solve. Well, so then what is the answer in string theory? And this is the Fuzzball paradigm which I wanted to explain. So first, consider a rough analogy. In 1982, Witten talked about something called a bubble of nothing, which some of you might be familiar with. So if you consider Minkowski space, I have just drawn one spatial direction here out of the 3 directions. But suppose there's an extra circle, so space is really 4 plus 1 dimensional. I just do the extra circle over here. This space-time is actually unstable to tunneling into a new topology, which is the following. This thing which looks like a drinking straw pinches in the middle and in fact separates. So this region in here is not a part of space-time at all. This part of the drinking straw closes smoothly here, and this part smoothly closes here, and you get into a new topology. This was a one-dimensional picture, but in higher dimensions, the following thing happens. You take space-time, remove a ball from the interior, let's say, of this room, and then the compact circle, which is living everywhere tensored with this space-time, as it approaches near the surface of the ball, it's not like you have a boundary of space-time where you fall in. As you come close, you smoothly close it off on all sides. And this compact to smooth manifold is, in fact, the bubble of nothing. So the normal Minkowski space-time with an extra circle is unstable to tunneling into this object. This itself was a bit of a curiosity because this topology was not allowed for theories with fermions. But now let us see what happens with black holes in string theory. The normal expectation was that if we take some bunch of strings and branes, we have to make the black hole from whatever is available in string theory. They would normally, at weak coupling, have a size which is order Planck size. But as we put strong coupling in there, it would just make the usual black hole. The strings would all go to the origin in some Planck scale little mess down there, and then the rest of it would be just the black hole. But now, actually, in 1 plus 1 dimensions, if I just draw the same thing, we of course have extra dimensions in string theory, so now drew it like a straw. And again, the expectation was the extra compact dimension, which might be Planck scale or something, wouldn't make much of a difference. You still get the horizon on both sides. This is what is happening at r equal to 0, and this is your space-time. But in fact, one finds that something quite different happens. In fact, instead of going into the kind of picture I drew on the previous page, it actually goes into something where this interior region of the horizon actually vanishes. The space closes smoothly here and here. Not in the very simple way that happened for the bubble of nothing. There's an extra angular twist which converts into a KK monopole, which is denoted by a plus here, or maybe an anti-monopole, which I denote by a minus. And so, in fact, the horizon and all the troubles associated with that, in fact, do not arise at all. In higher dimensions, again, the interior of the black hole horizon would be removed, and as you approach it from all sides, the compact dimensions form either a monopole or anti-monopole with other entities of string theory around them. So you get one sort of bit to choose per Planck area of the hole, which, as you can see, is roughly the number of states which you want for the entropy of the black hole. So what one is saying is that in string theory, there's something very simple to do. There's nothing to conjecture. It's a well-defined theory with no free parameters. Just take some bunch of strings and branes, put them together to make a large mass, and ask what kind of space-time it generates. And what you find is it does not generate the space-time which one naively expected, which is the one down here. It actually generates, it's not the one which you thought down here. You get the one which is of this kind, where the interior vanishes, and in fact, the space-time closes off just outside the horizon. So in fact, I'll draw the cartoon in this fashion. I won't keep drawing the compact dimension everywhere, but this interior region is not part of space-time. You don't end up getting this, you end up getting this, and now the whole thing actually has a surface. This has been checked out for many, many states by now, and in all the cases which have been checked, it always ends up looking like this. It doesn't ever end up becoming this. And so the Fuzzball conjecture would be that this thing continues, and there are no states of the black hole which are actually of this kind, and then the problem indeed would be solved. But as I said, at this point, you're entitled to ask, how did the space-time change in such a radical way? After all, a black hole is a very big entity. Shouldn't semi-classical approximations somehow have been a good guide to our understanding? Well, classically, if you take a star, you'd think it would collapse like this and make a black hole. You can put this in a computer, and you might ask, how does a semi-classical approximation ever get violated? But well, of course, there's a small amplitude, probability amplitude, for this collapsing star to tunnel and transition into one of these Fuzzball states. In fact, you can estimate that transition amplitude. It's of the order of e to the minus the classical action, which comes out to be e to the minus gm square. And in fact, using some old results of Cross, Wilczek, and Parekh, you can actually show it's of order exponential minus the Bekenstein entropy. So it's a very small number. But as I had said in the start of the talk, even though the amplitude transition from this to one of these states is very small, you now should multiply by the number of final states, which you always do when solving any transition amplitude in particle physics. And now you find that if you multiply this very small number by the number of states, which is e to the s Bekenstein, in fact, the small number cancels the large number, and you just get something of order 1. So in fact, a semi-classical approximation is actually broken in the theory of fuzzballs, because if you think of the whole thing as a path integral, indeed, there's a classical action which you normally extremize, and you say, well, the physics is basically given by this, and you ignore the measure at a classical order. But the measure counts the number of states that contribute to the process, and if the number of states is abnormally large, you know the Bekenstein entropy has a factor of 1 over h bar. In fact, you find that the measure is competing with the classical action. This is also s over h bar, and this also has a 1 over h bar. The two are exactly comparable, and the black hole is not a semi-classical object at all. Okay, so let me now get to the idea of complementarity, and how did that come about? So now we want to finally ask if there is some way to get our intuition for the ordinary black hole in. So suppose an energetic photon is trying to fall onto a normal black hole. Of course, it goes in, but now it's trying to fall onto the surface of a fuzzball. There is no interior, so there's no place for it to go in. So you might think the photon has hit like a brick wall or a firewall, and there is no place for it to go in. What should we do? But instead of saying that this is a firewall, there's actually a more interesting possibility, which is the idea of fuzzball complementarity. And here we will try to use, in the context of fuzzballs, the kind of ideas that were started off by 't Hooft and then later developed by Susskind, but with slight modifications required for the context that we have here, where we've actually found real degrees of freedom at the horizon. So the dynamics of infall into the black hole, like any quantum process, is described by certain frequencies. You can solve the wave equation for a particle falling in the horizon, and you can characterize that by some frequencies. I call them nu1 black hole, nu2 black hole, and so on. But if you hit the fuzzball, all that happens is you can oscillate the fuzzball surface. You can't go inside. There is no place to go inside. But the oscillations of the fuzzball are also described by some frequencies, which I have called nu1 fuzzball, nu2 fuzzball, and so on. Still having some difficulty with the pointer. But what happens if these frequencies, which you had up here, the nu1 black holes and so on, are the same set to a good approximation as the nu1 fuzzball, the nu2 fuzzball, and so on. If two systems have the same frequencies, then in fact, quantum mechanically, they are indistinguishable. You can just map one system into the other. So what we would like to see here as an explicit realization of complementarity is that if the vibration frequencies of the fuzzball surface are the same as the frequencies arising from solving the wave equation in the interior of the black hole, then in fact we have complementarity. Even though you actually cannot fall into the black hole, you still get the same dynamics when you fall onto the black hole surface. So if that is the case, then falling onto the fuzzball will feel approximately like falling through a classical horizon. Now this might look like a bit of a stretch. This looks like something a little bizarre. How could something like this ever happen? But something quite similar has been seen in a related context in the idea of ADS-CFT duality. Suppose you fall onto a brick wall, or just which I've drawn on the left here. I'm just wondering if I can use a different pointer. Okay, this pointer would work. If I fall onto let's say a concrete block, then of course I get shattered, I create random excitations, and I die. But now take a collection of, let's say, D3 brains, and you fall onto it. The D3 brains will vibrate, and you'll have excitations on the surface of brains which give these vibrations, but you can't go in. They're just some D brains. You fall on them, your energy gets converted to vibrations, and the D brains vibrate. But we know there is a different picture where you can replace these D brains by just anti-de Sitter space, and you smoothly continue falling into anti-de Sitter space. So here, of course, this was an exact map, but it's very important that in our case for the black hole, the map is only approximate. And why is that important? Because, in fact, this is how we get the information out. Every fuzzball surface was different, and that's why they all radiated differently. So if you look at low energy radiation, energy of the order of the temperature of the black hole, they are different for different fuzzballs, and the thing radiates just like a piece of coal, and the information comes out. But then if you hit it hard, if something falls freely onto the black hole, it reaches the black hole with an energy which is very high, and then the energies are much bigger than the temperature. Almost anything has an energy much bigger than the temperature. And then you get hydrodynamic oscillations of the fuzzball surface, which are not sensitive to which fuzzball you actually picked. And the frequencies of these, as we have conjectured, the frequency of vibration of this surface are approximately the same as the frequencies of infall into the black hole, and then this would be a realization of complementarity. So it's not an abstract idea anymore. You have explicit construction of what states you want. In principle, though I can't actually do it in practice, you can put the whole thing into a computer. You just throw something on it, it vibrates, and you see complementarity in this fashion. If it is true, at least the conjecture is now manifest in terms of a construction which can be checked. Okay, so let me come at the end to the concept of what is a firewall. So if you go to what Hawking showed us in 1975, and the kind of thing we just made precise in this theorem, which I said in 09, the whole thing is stable to small corrections. You can make it completely rigorous. This is what Hawking had argued. If the evolution of low-energy modes at the horizon is normal up to small corrections, he assumed the horizon was a vacuum, then he got his entangled pairs being produced, then you must have information loss or remnants. That was what Hawking showed us. Well, then if you just say, if a normal vacuum is going to give you information loss, that's the same statement as saying, if you don't want information loss or remnants, the horizon cannot be a normal place. So there must be some corrections around the horizon. So if you just go back to Hawking's original statement, in a sense, Hawking already told you the horizon can't be a trivial place. In fact, in string theory, we have found that it's not. We actually found the way the string states behave, they actually, the space-time ends at the horizon. So if this was already known, what are the AMS people actually telling us? What are they actually telling us new about the horizon? And as I said, what they really did was make a statement about complementarity. They added one extra assumption, assume that an infalling observer feels nothing but semi-classical physics till he reaches within Planck distance from the horizon. It looks like a very innocent kind of assumption. They do explicitly make it, but we'll see all the troubles actually come from there. If you make this assumption, then what they proved was that one cannot get the complementarity in the form proposed by Susskind. And what had Susskind actually said? He had said the information is returned from the surface of the black hole, but there's another picture in which the infalling observer, he just sees the vacuum as you fall through the black hole. So this was the idea of complementarity, the way Susskind was trying to do it, and these people basically went ahead and ruled that out. Now, the way they ruled it out was very simple. The whole firewall argument can be summarized in this one line. If there's some description in which the space around the horizon looks like the vacuum, then in that description, of course, you will create entangled pairs, and then you'll be back to the Hawking problem as before. Okay. So then you cannot have any complementarity because it's just a one-line argument. How can you get an exact vacuum at the horizon? But in fact, the kind of complementarity they were addressing is not the kind of complementarity you can ever have if you want to solve the information problem. We have already said that you have to focus on particles of energy E much bigger than T, because the horizon must be different when radiating particles of energy of the order of T, because that's how the information is coming out. So if you focus on particles of energy much bigger than T, only in that approximation you really want complementarity to come out. But what the firewall people were doing was they were not taking any such limits. They only, in fact, looked at particles of the energy of the order of T. But then, of course, you can't get information. And so the conclusion was a natural one. If you want the information to come out, then how can you get complementarity? But Fuzzball complementarity was the complementarity you get in this approximation, and that is not ruled out by their argument. But the other thing I want to tell you was that there is something rather strange about the assumption they made. They assumed that an infalling observer feels nothing but semi-classical physics till they reach within Planck distance from the horizon. In particular, the surface of the black hole does not respond in any way till it is hit by an infalling shell. Suppose you have a black hole, you throw another shell on it, till the shell reaches the horizon is not going to deform. This was the assumption they made when they were trying to rule out complementarity. But as we'll see on the next slide, this assumption actually violates a general belief that the entropy inside an area A should never be more than A by 4. So you can see that in one line from this picture. If you have, this is the horizon of a black hole, and these arrows represent a shell of matter falling onto the horizon. If the horizon responds only after matter hits it, and then maybe if it wants, it can expand, then suppose at this point the horizon already had an area A and an entropy equal to A by 4. The incoming shell brings in some more entropy. Suppose the incoming shell has an entropy S, then when this shell lands on this, before the horizon can expand, you still have an area A, but your entropy is S black hole plus S. So it's actually more than A by 4. So if you actually believe that within an area A, you should never have an entropy more than A by 4, you cannot use the operative, most crucial assumption that the firewall people used, and then the firewall argument actually does not work. Okay, so let me just put my summary up here. These are the things that I have told you. The original Hawking argument in fact, for the fact that there's an information problem is really an entanglement problem. As the pairs are created, the outside gets entangled more and more with the inside, and then if the inside vanishes, the outside left with no state at all. So the initial argument of Hawking, many people had thought there was something could be wrong with it. Maybe the trans-Planckian modes weren't handled quite properly, or maybe you had to worry about physics you didn't know, or maybe small corrections could fix it. But in fact, they were all put in the form of a theorem where you can make it completely rigorous, that in fact, as long as you have a horizon which to leading order gives physics like the physics in this room, then in fact, there is no way to solve the problem unless you have some completely new physics like massively non-local effects or violation of quantum mechanics or those kinds of things. So once you make the Hawking problem concrete in that fashion, you know that you need to change the horizon. But you have the theorem black holes have no hair, so what are you going to do? But the point is in string theory, you have novel things like extra dimensions, and now completely new topologies are possible. And what you find is if you take enough mass in string theory to make a black hole, the kind of geometry it creates actually lies in a new topology. The topology is not M3, 1 cross the compact dimensions. The compact dimensions actually make a non-trivial vibration over the non-compact dimensions, and the interior of the black hole actually vanishes. All the states lie in this new topology, in this new vibration, and those are the actual microstates of the black hole. In that situation, then of course, you actually have a surface to the object, just like the surface of a planet or a star, and there's no information problem anymore. It's just like burning a piece of coal, and the guy radiates from the surface. You might ask how the semi-classical approximation is violated on something as big as an astrophysical black hole, but there we saw that even though as you make the black hole bigger, the quantum effects keep becoming smaller for transition to any one of these novel new topology states. The number of these states also keeps growing the bigger the black hole you take, because they are e to the Becquerel entropy of the black hole. And this large number, the degeneracy factor, is always exactly canceling the smallness of the transition amplitude to any one fuzzball state, and so the black hole never actually becomes a classical object. You may still want to recover the classical picture for infall in some fashion, but then you recognize that when something falls into a black hole, by the time it reaches the horizon, it really speeds up. So it hits the black hole very hard, and then the black hole surface, this fuzzball surface, just undergoes oscillations, and the frequency of those oscillations, there are reasons to believe, which I haven't given you here, but there are reasons to conjecture that the spectrum of the fuzzball surface is the same as the spectrum of the gravitational waves or any object falling into the black hole. And if that is so, to a leading approximation, then you have a realization of the idea of complementarity, and then falling on the surface of the black hole, you can say you actually feel that you are going in to a leading approximation. Okay. I'll stop there. Thank you.
Questions, comments? Gerard? Microphone here.
It's a nice qualitative picture that you're giving, but as soon as you use the word complementarity, should you not also describe a transformation rule, a dictionary that tells you which states in one picture correspond to which state in another picture? And should that dictionary not also say something about causal order of events? What is causality? What is locality in both pictures?
Yes, that's a very good question. So let me tell you, yes, this is a qualitative picture. Some part of what I told you is qualitative. The actual quantitative hard calculation in this whole game are what I showed you in the beginning, the construction of the fuzzballs. We actually take states in string theory, we can actually make out those solutions, which these cap solutions which we make. That's the concrete part you can do. The rest of it is a picture put on it with estimates. So it just shows that that is possible. But in fact, indeed, for causality and so on, we have developed the picture, still qualitative, which shows you how causality happens, how something which fell in before is, in terms of vibrations, little behind something which happens after. When something falls on the surface, it starts dissipating. When something else falls later, it also starts dissipating, but things which have dissipated more are somehow deeper inside. So I'll be happy to show you that picture, but as I said, it's still qualitative. We cannot do the dynamics of these fuzzballs very well. We are at the stage where we basically construct them right now.
A related question is, this argument about large numbers, why does that not apply to ordinary quantum field theories, where you also do function integrals, where the number of states may also become very large?
I didn't catch the last part, where what is large?
In ordinary quantum field theories, the numbers of states you're talking about may also become very large when you do a function integral. So what's special about this large number argument as opposed to many other cases where, for some reason, it does not apply?
Yeah, I think what happened was that I don't actually know a case in field theory where the number is this large. So I should ask you what case that might be, because here what happens is the Beckstein entropy, in fact, is something which is so large that we are not able to reproduce with ordinary field theory models. If you take any model of particle physics with a finite number of particle species, we know, in fact, as you showed, the entropy can only go like a to the 3/4 and you never get a. So in fact, it's only when you get the entropy like a that this happens, because the action for class suppression goes like minus gm squared, that is fixed from the scale gm which comes in everything. But by no ordinary field theory can you ever get a, as in fact you yourself showed, you only get to a to the 3/4. So I think this case is special.
Thank you.
One last question. Just there. Yeah.
It's actually two questions. The first one is, do I understand you correctly that the information paradox is the string theory paradox, in the following sense that you can have remnant, like a baby universe, which can contain all the information. It just because string theory does not like this
Yes.
kind of remnant, it's a problem. So
Yes.
this is, I understood you correctly.
That is correct. That's correct.
Okay, so now I understand why some of the rest of us are less worried about this problem.
Okay.
Now, the second question is related in the following sense. What is the semi-classical structure of the space-time that you have near this fuzzball? I mean, because you're actually requiring now that you have a huge black hole, which can be a size of almost like the size of the radius of the orbit of the Earth around the Sun. And this object has now become a quantum object.
Yes.
So you are the one that, unlike what most of us thought, that quantum corrections would be on the Planck scale, you have now quantum correction on any scale.
Exactly.
And in this case, there are other proposals for for corrections like this that could resolve the problem. For example, the recent ideas by Bardeen. What makes this specific proposal better than these other proposals?
Okay, let me try to say something about that. Here what one has done is, maybe I should have said in the beginning, we're taking string theory as our theory of gravity, and with the theory we want to see how is the puzzle solved. Okay? So string theory, as I said, we don't have remnants, so I have ruled out remnants. Okay, we can't get that. And then what is special about these effects is when you sort of get them automatically. You take the strings and you see what it does, and it modifies the structure at the horizon. So it is not like you have to propose a new kind of long distance effect or some new effect. It is coming out of just normal local string theory and just normal local quantum field theory. It's just that if the density of states is very high and the measure factor starts competing with the action, it's not any new physics or new non-local effects you have to put in. It just happens automatically. So if you don't have string theory, if you take away my extra dimensions, I actually cannot make these new topologies which were going to give me all the solutions. But as you know, in string theory, I don't have a choice. I get the correct number of dimensions, and if somebody made string theory 9 dimensions instead of 10, actually the entropy of black holes that's done by Stronger of alpha, it was a beautiful calculation, exactly got the entropy right. It won't work. It will be off by a factor of 3/4. So in fact, you really have to use string theory exactly the way it stands, and that really comes in here. If I change any number in string theory, make a little mistake in my calculation, instead of getting a smooth closing to the space-time, I get either closed time-like curves or a conical defect, or the whole thing becomes unstable. Every number has to be exactly right for this topology to come out. So is it really something within string theory? This is just, you just turn the crank and you see what happens, and you're just trying to explain how in string theory automatically solves the problem. And just like happened with Strominger buffer calculation, if the entropy had not come out right, string theory would be gone. And I would say the same thing here. If it did not work out, string theory needs a solution. Otherwise, it would not be unitary.
Okay, I think we have to call this session to a stop. Thanking all the speakers.